this problem about two of our favorite physics teachers, Mr. Scholl and Mr. Forbes, standing on the edge of a cliff with height h. This was a test problem several years back. It was Mr. Rose and me because, um, well, we were there. So, edge of a cliff with height h at a time t naught, Mr. Forbes throws a rock directly upward at a speed of v naught, and Mr. Scholl simultaneously throws a rock directly downward with the same initial speed, v naught. So here is here they are, and for Mr. Forbes throws his up, and Scholl throws his down. So I want to show that both rocks hit the ground below the cliff with the same velocity. So several ways to do this. I'm going to show you all three of them. Algebraically, we can take the third cake equation, which is v final squared equals v initial squared plus 2a delta x. Now, this could be either of them. So v squared equals, I'm just going to plug in the values we have here, okay, v naught squared. And if we assume the cliff height, so the cliff height is like this, and then here's the base of the cliff, okay, so I guess I'm gonna make x point upwards, okay. So in this case, delta x equals negative h, and acceleration is negative g, okay. So v squared equals v naught squared plus 2 times negative g times negative h, so 2gh, okay. Now you will notice that if we do Forbes, this could be for Forbes's rock, or let me actually v for Forbes's rock squared, and it's initially launched at a velocity of v naught in the positive direction. Let me show you what it looks like for Scholl. For Scholl, well, it's the same thing, except his rock is initially launched downwards. However, because we're squaring this, the negative sign goes away, and both are going to have the same answer. So vf squared equals vs squared. And, you know, obviously this does mean that the final velocity of Scholl's rock and Forbes's rock could, this equation says they could have opposite signs, but we know that's not true. We know that if the rocks hit the ground, they're both going to have a downward velocity. So vf is equal to vs. And you could, of course, figure out what they are, but that wouldn't change the answer because they both get the same thing. In fact, I think for both of them, you'll get square root v naught squared plus 2gh, except actually the velocity would be negative because they're going down, okay? So anyway, that's how you do it algebraically. With a graph, what you can do here is say, okay, here is a plot, and I'm going to say, let's say they start, I'm going to do that. So here's the ground, here is x vertically, and there's time. Okay, so I'm going to do, let's see, I'm going to do Scholl's rock, or Forbes's rock in green, just because I feel like it, and I'm going to close that, great. So his is going to start here, and it's going to go up like this, and then arc down, and then go hit the ground, okay? Now, Scholl's rock, if you look at that, and I will do Scholl's in, I can do colors differently, can't I? Come on, there we go. Red, good enough. Scholl's rock is going to start off going down and then do that. And what you'd find, if I'd drawn these better, you would find that right here, draw this across, at this point, these two trajectories, once they pass through this line, look the same. So this is the initial height of the cliff, right? H, okay? That's slanty, it's not supposed to be. And so what happens is, when this guy goes up, Forbes's rock has an initial upward speed of v naught, and then when it passes through here, it's going downward at a velocity of v naught, okay? This is what happens. When you throw something up, it comes back down. It's got the same speed, but in the opposite direction. Its velocity is in the opposite direction when it passes back through the same altitude. So at this point, this rock here and this rock are the same, or they're going through the same state here, which means they're both going to take the same amount of time to reach the ground, okay? Which means they're both going to have the same velocity when they reach the ground. So what I'm saying is this section of this rock, of the red rock's path, and this section of the green rock's path are identical. They're both going to have the same velocity when they hit the ground. That's how you can do it with with a graph. The way you can do it with a short explanation is to say, well, what happens is, let's see, let me draw it over here. Shola's rock goes down and hits the ground. It's really basically the same as the graph explanation. You just do it differently by drawing like this, and you say, well, Forbes's rock has to first go up and then come back to the same height, and when it comes back to the same height, its velocity will have reversed. So now Forbes's rock goes down like that, and it does the same thing as Shola's rock. So that's a way you can explain that they go through the same state here, and so these two are going to be, these two are going to have the same final velocity. Okay, so that's sort of the three different ways you can do part A. For part B, find an expression for the time that passes between the two hitting the ground. What you'll find, you can do it sort of the straightforward way, where you say, I think, let's see, so you're going to do delta x equals v naught t, right, plus 1/2 a t squared, and you do delta x is going to be negative h for the rocks. Okay, so let's do Forbes's rock, you go v naught t minus 1/2 g t squared, and you could call this TF is time for Forbes, and this TF is time for Forbes. And then you can do the same thing for Shola. Now the difference for Shola is his rock goes through the same displacement. So again, for displacement, what matters is the difference between your ending point and your starting point. So the displacement for Shola's rock is the same as the displacement for Forbes's rock. In fact, that was sort of the fundamental thing that made this part work. Even though Forbes's rock does this extra up and down, the total displacement is still going to be the same. So for Shola now, he's throwing his down, okay? So his initial velocity is negative v naught ts, and then it's also going to be minus 1/2 g ts squared. Now you solve these two things for tf and ts, and it's tricky because you have to pick a different branch of the quadratic plus minus for each, but you can solve them and eventually find what that difference is. And then, so you take these two, and then you find tf minus ts. You can do that. I'll tell you, when we gave this as a test problem, not many people were able to do it correctly and keep it all straight and then come out with the right answer. The easier way to do it is to see that, look, what really happens, what really matters, the difference between the two is this time here, right? The time it takes Forbes's rock to go up and then come back down is the difference, because this amount of time for Shola's rock to hit the ground initially and the amount of time for Forbes's rock to go from here to here are the same, even though it doesn't look like it. This here and this here are the same. So what's really important is the gap between here and here, and that's going to be the same as here to here. And it's hard to find, this amount of time and then also find this amount of time and find the difference. But it's really easy to take a rock that's thrown upward and find how long it takes it to come back down to the same level. Because then you're just taking the second cake equation, and you're going delta x equals v naught t minus 1/2 gt squared. Well, actually, I guess if I'm doing it in the general form, it should be plus 1/2 at squared. And then when I plug in for this specific situation, I'm saying negative h. Oh, sorry, not negative h, because now we're trying to find the difference between this and this time, right? So the displacement is 0 equals v naught t minus 1/2 gt squared. So the two solutions to this, let's get this out to, let's see, v naught t equals 1/2 gt squared. So this is telling us how much time it takes the rock to go up and come back down. The two solutions, t equals 0, and this solution really is telling you that, well, obviously the rock will be at the same height if no time passes, but that's not the solution we care about. That's sort of the trivial solution. The real solution is v naught equals 1/2 gt, which you get when you factor out the t on both sides, and then you can get that the time it takes the rocks to, or it takes Forbes's rock to go up and then come back to this point, is just equal to 2v naught over g. can't, let me see. Oh, here's a little box tool. Let me see if I can box it with this. Oh, yeah. All right. So there you go. So that is the answer, if you can accept that that's a number 2 and not a Z. And I know that's kind of hard sometimes with my handwriting. But that's the answer to part B. And that's the easiest way to find it. Again, you could do it this way by solving these two and then finding this quantity. But, man, you're in for a world of hurt if you try. So there you go.